A femtosecond is 1/4,000,000th of a second. Or to put it another way, a femtosecond is 1/1,000,000th of 1/1000,000th of a second. A femtosecond is to a second what a second is to 32 million years. There are more femtoseconds in a single second than there are hours passed since the Big Bang. In fact, 8 times more. In a femtosecond, light travels just 300 nanometers. The femtosecond laser shoots pulses at femtosecond intervals, and that lets us observe fast-moving phenomena in physics, chemistry, and more as they happen. And out in the real world, the femtosecond laser has been used in things as varied as nuclear fusion to semiconductors to LASIK. It sounds impossible, but in today's video, the femtosecond laser breakthrough. But first, I want to remind you about the Asianometry Patreon. Early access members get to see new videos first with selected references attached. It really helps a lot. It's one of the best ways to directly support the channel, and I deeply appreciate all of you. Whenever I meet any one of my patrons, I try to buy them a coffee. Thank you, and on with the show. We cannot observe something fast unless we have something that can move faster. Imagine a falling droplet of water, a hummingbird's wings, or even a galloping horse. Without a sufficiently fast technology to capture this phenomena, it is all just a blur. So over the centuries, we have developed such technologies to quote-unquote slow down time. In 1857, the French physicist Edmond Becquerel, inventor of the solar cell, coiner of the name photoresist, contrived an instrument called the phosphoroscope. This thingy consisted of 2 spinning discs with holes in them. Becquerel placed a glowing substance between the 2 wheels, and by varying the wheel's rotation speed, he could visualize the phosphorescence of uranium salts at a speed of 1/2000th of a second. And then there was the thing about the horse. During a gallop, a horse's legs move faster than the human eye can perceive. This became a problem when artists throughout the ages tried to depict how a horse actually gallops. Unable to see how it actually happened, artists likely looked to doggos as a proxy. And since those good boys ran with all 4 legs outstretched in the air, they ported that to the horse, which led to some peculiar-looking artwork. In 1878, Edward Muybridge was commissioned by the robber baron Leland Stanford to photograph Stanford's favorite horse. Using a special spring-activated shutter that slowed things down to an estimated 1/1000th of a second, he produced a series of breakthrough photographs that revealed the movements of a horse's gallop in all of its herky-jerky glory. So, as it turns out, a horse does have all 4 legs out in the air, but not all outstretched like as a dog does. Rather, it happens with the legs all gathered together, like a dead cockroach. Muybridge later used his multi-camera setup to create what is essentially a movie. Many years later, this movie technology would be used to record a victory by the UC Berkeley football team over Leland Stanford's University football team via a last-second game-winning kickoff return called The Play. Go Bears. In 1899, Max Abraham and Georges Lemoine produced an ingenious experiment bringing time resolution down to the nanosecond. Their experiment takes advantage of something called the Kerr effect. First discovered back in 1875 by the Scottish physicist John Kerr, this describes when certain materials rapidly change their refractive index when an electric field is applied. We can use this to create something called a Kerr cell shutter. It works by using an electric field to rapidly change the refractive index of a chemical like nitrobenzene. Abraham and Lemoine's 1899 experiment activated a spark and a Kerr shutter at the same time, allowing them to conclude that the Kerr effect of carbon disulfide lasted less than 10 nanoseconds. Later experiments found its actual timing to be 2 picoseconds. Kerr cell shutters were used by NASA's Jet Propulsion Lab in the 1950s as fast shutters, far faster than mechanical ones, for high-speed cameras capable of recording up to 50,000 frames per second. Their high speed would also be useful in other technologies to be mentioned down the line in this video. Then, in post-war Britain, 2 Cambridge chemists, Ronald Norrish and George Porter, introduced the technique of flash photolysis in 1949. Their technique used two brief flashes of light to probe high-speed chemical reactions. The first flash to stimulate some photo-induced chemical reaction, then a second mechanically triggered flash right after that to read the reaction using stereoscopy. Along with the German chemist Manfred Eigen, Norrish and Porter founded the field of microchemistry, the study of fast-moving chemical reactions at the microsecond level. In 1967, the three chemists together won the Nobel Prize in Chemistry. Several felt at the time that these immeasurably fast time resolutions, microseconds verging even on nanoseconds, would be the fastest ever measured. Luckily, the laser proved them wrong. The first functional laser was invented in 1960 by Theodore Maiman. That device worked by a ruby crystal, which is the gain medium, energized by a xenon flash lamp. The ruby gain medium then produces light, which is amplified within a cavity before being sent out towards its target. The 1960 ruby laser's pulse intervals lasted between a micro and millisecond. Was there a way to reduce that yet further? An early method to do so was Q switching, first demonstrated in the early 1960s by Robert Hellwarth. With this, we manipulate the Q factor of a laser's cavity up or down to create a pulse. If you recall, the laser cavity stores and focuses the laser light coming out of the gain medium. It can be as simple as two mirrors facing one another, one fully reflective and the other partially so. When the light gets strong enough, it bursts through the partially reflective mirror and to the target, a laser. The Q factor describes how well the cavity stores that light's energy as it bounces back and forth between the two ends. A high Q score can maintain energy without large losses. A low Q score, no. So if we rapidly switch the Q score up and down, we can rapidly influence the cavity's ability to laze, creating the pulse. I have seen it described as like holding your thumb on the end of a garden hose to get a pulse of water. This was done in the day by inserting something into the cavity. Hellwarth suggested a Kerr cell shutter, like the one we talked about earlier, to modulate the light and generate giant pulses of duration of about 10 nanoseconds. Others reported similar results with a set of rotating prisms mechanically driven by a turbine. Those methods worked fine, but to get down to the next level of ultra-short pulses, we needed something else. The method that drastically brought down the laser pulse interval was mode locking. Let me try to explain this one. Let us go back to the laser cavity with the light bouncing back and forth between the two mirrors. With ordinary lasers, the gain medium, the ruby crystal, emits a whole range of light across frequencies. But the laser cavity's physical properties make it so that only a certain cluster of frequencies can build up inside. Each of these frequencies is called a mode. You might want to think of it as like the strings on a violin. Light and sound are both waves. Each string can create a variety of different sounds, though not all sounds can be made by each string because that depends on the violin's physical characteristics. In the same way, a laser has many modes. In an ordinary laser, these modes are random, influenced by things like temperature and the whims of the gods. The result is pretty much just a constant noise. But it doesn't have to be. Mode locking is where you try to get these modes together so that they constructively interfere with each other to get these short, consistent pulses. Mode locking was first demonstrated in 1964 when a Bell Labs team led by Hargrove, Fork, and Pollack published their success in mode locking a helium neon laser. This was done by lightly applying acoustic waves to the medium inside the laser cavity. This changed that cavity medium's index of refraction, which in turn varied the path of certain modes of light waves bouncing back and forth inside. What does that mean? So here is a second, very rough metaphor. Imagine a bunch of sprinters running back and forth on a track. Normally, if things are as they are, then the sprinters finish the race at a distribution that is essentially random, dependent on their own properties. Sometimes you get a few randomly crossing the finish line together, and that's a pulse via constructive interference, but on the whole it's random noise. But if we can undemocratically force each of the sprinters to modify their speed on the track, we can coordinate them to cross the finish line in synchronized bunches. That is what the Bell Labs team did with these acoustic waves. The result was a series of pulses spaced at well over 1 nanosecond, the time it takes for the light to do a round trip inside the cavity. Good start, but 1 nanosecond was not that impressive. This was because the helium neon laser is limited in the wavelengths it can amplify, as in, it can put fewer runners on the track, which makes the pulse intervals longer. In the years afterwards, researchers worked on ways to further cut the pulse duration. In 1966, A.J. Demaria demonstrated a self-locking laser that cut the interval to below 1 nanosecond. There, things paused for a few years. One major problem was that this mode locking was highly sensitive to the laser's conditions, creating inconsistent pulses. We needed a way to make the pulses more repeatable. In 1972, two more Bell Labs researchers, Eric Ippen and Chuck Shank, lots of Bell Labs people in this video, discovered a way and used it to break the picosecond barrier. They built a laser utilizing two special dyes, pumped or energized by a continuous argon laser. A complicated setup of 5 mirrors, extensions, and prisms helped tune the light's paths throughout the whole setup to achieve the proper mode locking. 2 years later, a second generation of this setup achieved pulses of less than 1 picosecond, officially entering the femtosecond era. And then in 1987, a dye laser of this setup produced a pulse as low as 6 femtoseconds, though the average was more in the range of 10 to 100 femtoseconds. Groundbreaking work in theory, but in practice, these early dye lasers did not really set the world on fire because they were big, expensive, and difficult to use. Moreover, they require thin films of saturable dyes just a few micrometers thick. These organic dye materials had environmental and health concerns. Not only were they toxic, but they also needed frequent replacement because they are organic and broke down often due to exposure to bright light. And lastly, the laser output was underpowered, necessitating the use of separate amplification stages to ramp up their power. University labs did not really leap to use these things for their research. This all changed with the rise of a new type of laser. In 1986, P.F. Moulton published work discussing the laser-like characteristics of a new type of titanium-doped sapphire crystal. His research traces back to stuff done at the MIT Lincoln Laboratory in the early 1980s as a potential dye laser replacement for spacecraft. What a success that was. The titanium-doped sapphire laser became widely used for scientific research because the crystals are solid and robust, emit a wide range of light, and can operate at room temperature. By itself, the titanium sapphire laser is continuous, but soon after its commercialization in 1990, researchers at the University of St. Andrews, led by the recently passed Wilson Sibbitt, discovered that they can get a titanium sapphire laser to self-mode lock without needing those external dye modulator setups. This happens via the aforementioned Kerr effect. Recall earlier in this video that is when an electric field changes the material's refractive index. In this variation of the Kerr effect, dubbed the optical Kerr effect, intense light falling onto a crystal creates an electric field that modulates the crystal's refractive index, in effect, allowing the crystal to self-focus its light. This new variation of the Kerr effect was interestingly discovered many decades after the original. Goes to show how much more there is to know about our world. This self-focusing effect is harnessed to create the Kerr lens mode-locked, or KLM, titanium sapphire laser, which first hit pulse intervals of under 10 femtoseconds in the late 1990s. By 1995, the interval record was pushed down again to 6 femtoseconds, 2001 to 5 femtoseconds. Combined with a second methodology to amplify the power levels of these lasers by stretching and compressing the pulses, called chirped pulse amplification, this fully unlocked the laser's power for scientific research. I'm going to stop here because the ecosystem of ultra-short pulse lasers has since exploded over the years. In addition to the KLM technique, There's been the semiconductor saturable absorber mirror, or SESAM technique. In addition to titanium sapphire lasers, we have ytterbium doped yttrium aluminum garnet and ytterbium doped potassium yttrium tungstate lasers. That's a mouthful. And these can be produced as thin disc lasers, where the laser gain medium is turned into a disc rather than a rod for thermal and power reasons. I can keep going and going and going like the Duracell bunny. I'm pretty sure I've lost a lot of you by now. I must admit that this history of pulse laser development, simplified as it was, can be rather difficult to follow, and it might get easy to start asking yourself, what's the point of all this? The invention and commercialization of the femtosecond laser gave us a powerful camera to glean groundbreaking, Nobel-winning insights into things that previously were too fast to see. Let me shout out the work of the late Dr. Ahmed Zewail, an Egyptian-American chemist from Caltech. For all the centuries chemists have been doing chemistry, they could never observe chemical reactions as they happened in real time. They happen too fast. Atoms move at 1 kilometer per second, and since we're talking about distances of just a few angstroms, we needed cameras with time resolutions of about 100 femtoseconds to see anything. So Zewail updated the venerable flash photolysis methods, which dealt in mere microseconds, for the modern age. He shot femtosecond pulses of laser light at molecules to probe fast-moving chemical reactions, creating essentially films to see the horses gallop. His work won the 1990 Nobel in Chemistry, making him the first Arab to earn a Science Nobel. A few years later, the femtosecond laser contributed a 2005 Physics Nobel. By bringing our time slices down to the femtosecond, it has given scientists the precision to measure and compare the optical frequencies of certain light waves that previously oscillated too fast to observe before. Okay, so femtosecond lasers are glorified measuring sticks with extra notches on them. How about some real benefits, right? Then feast your eyes on the impact that ultra-short pulse lasers have had on medicine. Femtosecond lasers are the sharpest and most precise of scalpels, particularly for eye surgery. Femtosecond lasers can vaporize small amounts of tissue while minimizing damage from shock waves and cavitation gas bubbles of water and carbon dioxide. I'm sure the 800,000 or so people getting LASIK each year appreciate that it's now done with these lasers rather than crude metal sharp things. And femtosecond lasers let us generate a whole new wavelength of radiation. Terahertz waves, or T-rays, sit between the infrared and millimeter wave bands. Like X-rays, they can pass through clothing, paint, and paper, but with fewer radiation concerns because they are non-ionizing. But for decades, T-rays were hard to produce, creating what was called the terahertz gap. Femtosecond lasers close the gap by enabling a method known as terahertz time domain spectroscopy, or terahertz TDS. In terahertz TDS, a femtosecond laser fires pulses at a device called a terahertz emitter, which is a switch with a gap in it attached to a small antenna deposited on top of a semiconductor material. The gap within the switch is usually highly resistive, but when hit by a femtosecond laser pulse, it becomes conductive, and charge carriers can now flow across it for just about 1 picosecond. This creates your terahertz signal. And today, terahertz TDS remains the most commonly used method for producing terahertz radiation, with large use case applications in automotive and semiconductor manufacturing. I started this video thinking that I would just be exploring a cool laser technology. How did I know that I was going to end up diving into the very essence of time? But it sort of makes sense to me that we need some yardstick or timer or camera so to observe these types of fast-moving phenomena. The femtosecond breakthrough fed a generation of science and technology applications, but now we're moving on. For all their speed, femtosecond lasers are not fast enough to capture the movements of electrons. So we need to go deeper. Recently, the 2023 Nobel Prize in Physics was awarded to 3 scientists whose research and experiments have shown how to create attosecond light pulses. Attoseconds are 1 quintillionth of a second. Quintillion. Incredible work, and something perhaps I will cover more down the line. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.